Section: Introduction. In this section, we explore the optimal model size and number of training tokens for training a transformer language model within a specified compute budget. We conducted training on over 400 language models with parameters ranging from 70 million to over 16 billion and trained on 5 to 500 billion tokens. Our findings suggest that for efficient training, the model size and number of training tokens should increase at the same rate. This means that as the model size doubles, the number of training tokens should also double. We developed a model named Chinchilla based on these findings, which we refer to as Chinchilla Scaling laws. We used 3 different methods, approaches 1 to 3, to estimate the optimal compute frontier. These methods involve training models of fixed sizes on varying numbers of tokens, training models of different sizes to meet fixed compute budgets, and fitting a parametric model to understand the relationship between model size, training tokens, and loss. Our key result indicates that for efficient training, the model size and the number of training tokens should scale equally. This finding has been supported by other studies as well. Approach 3 is particularly interesting as it helps us understand the parametric form of scaling laws for dense transformers. We attempted to replicate this approach by fitting a parametric function to model the final pre-training loss based on the number of model parameters and training tokens. Our analysis revealed significant differences from previous findings, indicating that their fit did not accurately describe the data. We also found inconsistencies with scaling policies derived from other approaches. By extracting data from a previous study's Figure 4, we reconstructed the scatter plot of language models based on model size, training flop, and loss value. This involved converting the data from a PDF to SVG format and extracting information on model sizes, training flop, and loss values from the scatter plot. Despite potential errors introduced during the digitization process, our analysis identified certain data points with high loss values for models with low training token to parameter ratios. These anomalies require further investigation to understand the reasons behind the unexpectedly high losses in these cases. Section Summary. In this section, we investigate the optimal model size and number of training tokens for training a transformer language model within a given compute budget. We find that for compute optimal training, the model size and number of training tokens should scale equally, doubling in tandem. By training a model named Chinchilla based on these findings, we established the Chinchilla Scaling laws and explore different methods to estimate the compute optimal frontier, shedding light on the parametric form of scaling laws for dense transformers. Section: Hoffmann et al.'s Approach 3 Replication Attempt. In this section, we applied Hoffmann et al.'s parametric scaling law to our subset of the data. We used the Huber loss minimization method to fit the function, following Hoffmann et al.'s approach. We set the parameter delta to 0.001 and initialized alpha, beta, E, A, and B over specific ranges. This led to our estimated model, which showed differences from Hoffmann et al.'s estimates. To test the significance of these differences, we considered the covariance between the estimates. By estimating the covariance matrix using bootstrapping, we found that the differences were highly statistically significant. Specifically, parameters E and beta showed significant deviations from Hoffmann et al.'s values. On the other hand, parameters A, B, and alpha did not differ significantly. When comparing the residuals of our estimated scaling law with Hoffmann et al.'s, we found that our model provided a better fit to the data. Our model had lower loss values for the majority of observations, indicating its superior performance. A likelihood ratio test confirmed that our fit outperformed Hoffmann et al.'s estimate significantly. The discrepancies between the two models were unlikely to be due to noise in our data reconstruction, as even adjusting Hoffmann et al.'s estimate of parameter E did not improve the fit. A Kolmogorov-Smirnov test further supported the conclusion that our model better captured the data. Section Summary. In this section, we fit Hoffmann et al.'s parametric scaling law to our subset of data by minimizing the Huber loss with specific initializations. Our estimated model differs significantly from Hoffmann et al. S, especially in parameters E and beta, showing substantial deviations. The Chinchilla scaling law fails to fit the data well, with our model performing significantly better based on various statistical tests, indicating potential issues with Hoffmann et al. S estimated scaling law. Section. Hoffmann et al. Report implausibly narrow confidence intervals. In this section, we discuss Hoffmann et al. S findings on optimal scaling relationships. They reported very narrow confidence intervals for parameters A and B, which are crucial for understanding how to allocate a computational budget C effectively. The relationships n_opt, propto C_A, and d_opt, propto C_A, show the best way to allocate training compute. Hoffmann et al. Reported confidence intervals of 0.454 to 0.455 for A and 0.542 to 0.543 for B, which are remarkably tight considering they had around 400 observations. In contrast, we estimated a standard error of 0.018 for A, resulting in an 80% confidence interval width of approximately 0.05, 50 times wider than Hoffmann et al. S reported interval. To achieve a confidence interval of 0.001, we would need about 600,000 training runs, significantly more than the likely 400 to 500 data points used by Hoffmann et al. Further clarification from the authors on this matter would be beneficial. Our confidence interval for A aligns with approaches 1 and 2 in Hoffmann et al., indicating consistency in our optimal scaling policy with theirs. We determined the compute optimal scaling policies, considering the uncertainty in our estimates, leading to a range of policies shown in figure. Two key observations emerged. Firstly, Hoffmann et al. S confidence intervals for optimal scaling policies were excessively narrow given the reported data points. Secondly, their scaling policy suggested using around 70 tokens per parameter, contradicting the 20 tokens per parameter ratio they used for training. Our model suggests an optimal ratio of about 20 tokens per parameter, consistent with practical training and findings from approaches 1 and 2 in Hoffmann et al. The discrepancy between the scaling law estimates in approach 3 and the results from approaches 1 and 2 raises concerns about the accuracy of Hoffmann et al. S parameter estimates. Our alignment with the token-to-parameter ratio used in practice and from their other approaches supports the validity of our fit. We identified 3 issues with Hoffmann et al. S estimates: poor model fit to the data, implausibly tight confidence intervals given the data points, and an inconsistent scaling policy compared to their other approaches. These discrepancies warrant further investigation. Hoffmann et al. S paper has had a significant impact on the language modeling community, influencing scaling policies of models like Google's Gemini suite. It is crucial to ensure the robustness and reproducibility of such influential research. Our work underscores the uncertainty in compute optimal scaling, showing a consistent model fit with a token-to-parameter ratio between 4 and 40 for models trained on 1E26 flop or more. Obtaining tighter estimates before large experiments could lead to substantial compute savings.